There are very few things in life that feel truly safe. Chairs usually hold us. The floor usually stays where it is. And no matter how strange the world becomes, no matter what happens in the news, in the sky, or in your group chat, 1 plus 1 is still 2. It is possibly the most comforting fact humanity has ever agreed on. You can forget your passwords. You can forget where you put your keys. You can forget why you walked into the kitchen. But somewhere deep inside your brain, glowing softly like a nightlight, lives the idea that one thing plus another thing makes two things. It feels so obvious that it barely feels like knowledge at all. It feels more like a reflex, like blinking, like breathing, like getting annoyed when someone says literally wrong. And that is why this story exists. Because at some point a group of very serious adults sat down and decided that this obvious thing, this warm, familiar, trustworthy little equation, needed to be proven, formally, carefully, from nothing. And that proof took 360 pages. If that turns out to be wrong, we are in trouble. Now, before your brain starts doing that thing where it panics and says, "Oh no, this is math," let me reassure you of something very important. You do not need to understand any math to be here. You do not need to remember anything. You do not need to solve anything. You do not need to prove anything to anyone. This is not a lesson. This is a story about humans, about certainty, about overthinking, and about what happens when you refuse to let even the simplest idea go unquestioned, because humans are strange like that. We are the only species that looks at something that works perfectly fine and says, quietly, at first, yes, but why? At some point, very early on, 1 plus 1 was not a statement. It was an action. You had one apple. Someone handed you another apple. Now you had 2 apples. No debate. No footnotes. No angry letters to academic journals. Just apples. And yet, thousands of years later, someone would look at that same idea and say, I would like to rebuild this entire concept from absolute zero just to be sure, which raises an uncomfortable question. If 1 plus 1 equals 2 is so obvious, why does it even need to exist as a statement? We don't say breathing in plus breathing out equals still alive. We don't prove that standing on the ground keeps you from falling into space. We don't write books explaining why water is wet. Some things are so deeply baked into reality that they feel immune to doubt. And yet, math has a problem. Math does not trust vibes. Math does not care how obvious something feels. Math does not care how many times something has worked before. Math does not care that you learnt it when you were 5 and have been emotionally attached to it ever since. Math wants receipts. And not just any receipts. Perfect receipts. Receipts that go all the way down, because once you start building complicated ideas, once you start stacking concepts on top of concepts, you start to worry. What if the foundation is shaky? What if there is a crack at the bottom that nobody noticed because it felt too silly to check? Imagine building a skyscraper on top of a chair. The chair has always held you before. It seems fine. You trust it. But once you add 30 floors, suddenly someone asks, "Hey, has anyone actually checked the chair?" That is where this story begins. Not with genius, not with madness, but with anxiety. The very human anxiety of wanting to be absolutely sure. Because math is a strange kind of safety net. It promises that if you do everything correctly, if you follow the rules, if you never make a leap you can't justify, then the conclusion will be unshakable, true forever, true everywhere, true even if the universe decides to do something weird. And 1 plus 1 equals 2 feels like the strongest possible candidate for that kind of truth. It feels ancient. It feels universal. It feels like something even aliens would agree on after a brief meeting and a cup of tea, which makes it deeply unsettling to learn that at some point mathematicians realized they had never actually proven it. Not in the way they now demanded proof. They had assumed it, used it, built entire civilizations on top of it. But assumption is not proof. And math, once it learns a new standard, does not forgive the past. So this is the beginning of a very slow unraveling. A journey that starts with comfort and ends with 360 pages of dense logic, careful definitions, and a man who thought about things just a little too hard. But for now, we stay here, with the simple version. One thing, another thing, 2 things. Your brain likes this because it is predictable. Predictability feels safe. Safety feels good. That is why counting is one of the first games humans invent. Children count steps. Sheep get counted at night. People count days, years, mistakes and regrets. Counting is how we impose order on chaos, and 1 plus 1 is the smallest possible promise that order exists. So take a moment to enjoy that. This idea has survived ice ages, empires, plagues, revolutions, bad hairstyles, and social media. It has been whispered, shouted, carved into stone, written in chalk, printed in textbooks, and now spoken quietly into your ears as you slowly drift towards sleep. And yet, despite all that history, despite all that confidence, someone once looked at it and said, "I'm not convinced." And that is where things start to get interesting. Because the moment you stop trusting even the most obvious truth, you open a door. Behind that door is logic. And behind logic is obsession. And behind obsession is a 360-page proof that will eventually, triumphantly, inform you that yes, 1 plus 1 really does equal 2. But not yet. For now, let's stay with the comfort. Let's stay with the obvious. Let's stay with the idea that some things are so simple they feel like they shouldn't need to be said at all. Because soon, very soon, we're going to ask the most dangerous question mathematics has ever asked. What is a number? And once that question is out in the open, there is no going back. Before math became something you could fail at, it was something you could hold. You didn't study it. You didn't write it down. You definitely didn't worry about proofs. You just counted things. Early humans did not wake up one morning and say, "Today feels like a good day to invent numbers." They woke up hungry. They woke up cold. They woke up needing to know if all the animals were still there. This is where math begins. Not in classrooms, not in books, but in survival. Imagine standing in a field thousands of years ago. You have sheep. You really like these sheep. They keep you warm, fed, and alive. So you count them. One sheep, another sheep, another sheep. At some point, you stop because the number feels right. And then the sun sets. The next morning, you count again. One sheep, another sheep. And then you stop early. Something is wrong. This is not philosophy. This is not abstraction. This is panic. Math did not begin as an intellectual exercise. It began as a way to notice that something was missing. Early counting systems were physical. You used your fingers, your toes if things got serious. You used stones, scratches on wood, knots in rope. One sheep went out. One stone went in your pocket. Simple, reliable, very hard to argue with. And when you added a sheep, you added a stone. That is 1 plus 1. Not a statement, not a rule, just an action. Two things meant two objects you could trip over. This is why 1 plus 1, 2 feels so deep in your bones. It was never theoretical. It was weight. It was sound. It was movement. You could hear two footsteps. You could feel two hands. You could see two fires burning instead of one. There was no room for doubt. If you had one apple and someone gave you another apple, you did not debate the nature of addition. You ate both apples. This is also why early math had no patience for cleverness. Nobody cared about elegance. Nobody cared about generalization. Nobody cared about being impressive. They cared about not starving. Counting was not about intelligence. It was about memory. And memory is unreliable. People forgot things. People miscounted. People lost track. So they externalized numbers, marks on bones, notches in sticks, little piles of pebbles. Math was born the moment humans decided they no longer trusted their own brains, which is, honestly, very on brand. And this kind of math did not ask questions. It did not wonder what a number really was. It did not worry about definitions. It worked. If you had 2 spears, you could hunt bigger things. If you had 3 people, you could lift heavier rocks. If you had 5 enemies, you should probably run. Addition was movement. Subtraction was loss. Multiplication was more hands. No symbols required. And when mistakes happened, they were obvious. If you thought you had 5 sheep and only saw 4, the problem was not philosophical. The problem was that something had eaten your sheep. So for a very long time, math stayed close to the ground, It stayed close to dirt, blood, fire, and food. And for most of human history, this was enough. But humans have a habit. Once something works well, we start playing with it. We notice patterns, we generalize, we abstract. We ask, what if? What if we didn't need the sheep anymore? What if we could count without objects? What if numbers could exist on their own? This is the moment where things begin to drift. Because the moment you remove numbers from physical objects, they become strange. What is 2 if it is not 2 apples? What is 1 if it is not 1 hand? At first, this doesn't matter. You can still picture it. You can still imagine sheep if you need to. But imagination is a slippery place, and eventually people started doing math with things that could not be held. Days, and stars, distances, time. You can't put time in your pocket. You can't tie a knot in a star. And yet, somehow, 1 day plus 1 day still felt like 2 days. The old intuition kept working, which made everyone very confident. Maybe too confident. Because while counting sheep teaches you how numbers behave, it does not teach you what numbers are. It teaches you results, not foundations. And as long as math stayed small and practical, that was fine. But humans are not known for stopping at fine. We build towers. We build systems. We build entire worlds of ideas. And once math started to grow beyond survival, once it became a language for describing everything, the old comfort started to crack. Because the stones in your pocket can tell you how many sheep you have. They cannot tell you why counting works at all. And that question sat quietly for centuries. Nobody rushed to answer it. After all, math was working. And when something works, humans tend to leave it alone. Until it doesn't. But before math became anxious, before it became philosophical, before it started demanding proofs and axioms and certainty, it was just counting. Just hands and fingers. Just piles of things. Just the quiet satisfaction of knowing that if you had one thing, and then another thing, you now had 2 things. No books. No symbols. No 360-page proofs. Just sheep. And stones. And the comforting belief that the world could be measured even if we didn't fully understand why. But that belief would not last forever, because eventually someone would ask a question that sheep could not answer. A question that fingers could not hold. A question so simple it sounded harmless. What is a number? And once that question was asked, math would never be simple again. At first, the question sounds harmless, almost cute. What is a number? You've known numbers your entire life. They've followed you around since childhood. They show up on clocks, phones, doors, birthdays, bank accounts, and receipts you pretend not to look at. Numbers feel familiar, friendly, even. Which is exactly why this question is so dangerous. Because the moment you stop asking what numbers do and start asking what numbers are, everything gets quiet. Uncomfortably quiet. If you asked an early human what a number was, they would probably just point. 2 stones, 3 sheep, 5 people standing behind you with sticks. Problem solved. But as soon as numbers drifted away from physical objects, as soon as they became symbols written in dust or ink, they started to float. And floating ideas have a habit of becoming strange. Take the number 1. What is it? Is it a thing? An idea? A label? A sound we all agreed on? When you say 1, nothing appears in your hand. You have to imagine something, which means numbers, at least partly, live in your head. And that makes people nervous. Some thinkers were perfectly comfortable with this. Plato, for example, loved the idea that numbers were real in a deep eternal way. Not real like rocks or sheep. Real in a purer sense. According to Plato, numbers existed in a perfect invisible world of ideas. A realm where circles were perfectly round, triangles were flawless, and the number 2 was always exactly 2, no matter what happened down here in messy reality. In this view, numbers are discovered, not invented. We don't create them. We stumble upon them, like cosmic furniture that has always been there. This is a very comforting idea. It means math is not arbitrary. It means 1 + 1 = 2, because it has to, not because we decided it. But not everyone liked this. Other thinkers looked at numbers and saw tools, human inventions, useful, clever, but not sacred. In this view, numbers are more like language. We made them because they help us communicate and organize the world. And like language, they only work because we agree on the rules. This idea is also comforting, just in a different way. But here is the problem. Math wants certainty, and certainty does not like vague answers. Are numbers real things that exist independently of us? Or are they clever inventions that happen to work really well? Because if numbers are invented, then math rests on human agreement. And human agreement has a terrible track record. If numbers are discovered, then where are they? You can't point to them. You can't weigh them. You can't trip over them in the dark. And yet they seem to obey rules no matter who looks at them. 2 + 2 = 4, whether you like it or not. This tension sat quietly for centuries. Most people ignored it, because again, math was working. You could build buildings, predict eclipses, collect taxes. Nobody really wanted to poke the philosophical bear until math started to grow ambitious. Once mathematicians began exploring infinity, imaginary numbers, and abstract spaces, the old explanations started to wobble. You could no longer rely on sheep. You could no longer rely on fingers. You had to rely on definitions. And definitions are dangerous things, because the moment you define something, you expose your assumptions, and assumptions are where cracks begin. So mathematicians tried to be careful. They tried to define numbers in ways that felt solid. But every definition raised new questions. If a number is an idea, where does it live? If it's a symbol, what gives it meaning? If it's a collection of things, what happens when there are no things? This is where math starts to feel less like counting and more like philosophy. And philosophers, historically, love this part. They enjoy sitting very still and arguing about things nobody can see. Mathematicians, on the other hand, are practical idealists. They want results. They want systems that work. They want to know that when they write something down, it means the same thing tomorrow. So they tried to push the question aside. They said, in effect, we don't need to know what numbers are, as long as we know how they behave. This worked for a while, but deep down the question kept humming. What is a number? Because once you admit that you don't really know, a disturbing possibility appears. What if the rules you rely on are based on intuition rather than certainty? What if 1 + 1 = 2? Because it feels right, not because it has been justified from the ground up. For everyday life, this does not matter. You will not wake up one morning to find that 2 cups of coffee have merged into 1. Reality is very forgiving, but math is not about what usually happens. Math is about what must happen, always, without exception, and must requires more than habit. It requires structure. It requires logic. It requires starting from something so basic, so unquestionable, that everything else can safely stand on top of it. And this is where the catastrophe begins. Because once you start looking for something unquestionable, you realize how little actually qualifies. Even numbers, especially numbers. The more carefully you look at them, the more they slip through your fingers. They behave perfectly. They follow rules. They give answers. But their existence remains oddly mysterious. And that mystery makes mathematicians uncomfortable. So uncomfortable, in fact, that some of them decided to do something drastic. They decided to rebuild numbers from scratch. Not using sheep, not using intuition, not using common sense, but using logic alone. Pure, cold, careful logic. The kind that does not care how obvious something feels. The kind that asks for proof, even when everyone else is already nodding. And once you commit to that path, once you decide that nothing is allowed unless it is defined and justified, you create a problem for yourself. Because now even the simplest question becomes complicated. Now, even 1 + 1 must earn its place. And soon, very soon, we are going to meet the person who took this discomfort personally. The man who looked at numbers, logic, and certainty, and decided that the only acceptable solution was to prove everything. Even the obvious, especially the obvious. But before that, we need to understand the system that made this obsession possible. A system that promised certainty. A system that turned intuition into rules. A system that would quietly, accidentally break everything. And that system begins with a man named Euclid. Euclid did not mean to cause problems. In fact, he was trying to do the exact opposite. He wanted order. Around 300 years before the Common Era, Euclid sat down and did something very human and very dangerous. He tried to organize knowledge. Specifically, he tried to organize geometry, shapes, lines, angles, the kind of math you can draw in the sand with a stick. At the time, people already knew a lot about geometry. They knew how to measure land. They knew how to build things that didn't fall over. They knew how to make shapes behave, but this knowledge was scattered. Bits of insight here. A clever trick there. Rules passed down without explanation. Euclid wanted to clean this up. So he wrote a book called Elements. And Elements did something revolutionary. It did not just list facts. It built them. Euclid started with a small set of statements that he called axioms. Things so obvious they did not need proof. A line can be drawn between 2 points. Things equal to the same thing are equal to each other. If you add equals to equals, the results are equal. Simple, comfortable, familiar. From these, Euclid derived everything else. Theorems followed from axioms. Results followed from definitions. It was neat, elegant, satisfying in a way that made the human brain very happy. For the first time, math looked like a machine. You put axioms in at the top. You turn the crank. Truth came out the bottom. This was incredibly powerful. It meant you no longer had to trust tradition. You no longer had to trust authority. You didn't even have to trust your own intuition. You just had to trust the system. And for centuries it worked beautifully. Elements became one of the most influential books ever written. People studied it for over 2,000 years, not because it was exciting, but because it felt certain. This is where the problem begins. Because Euclid made a quiet promise. He promised that if you started with unquestionable truths and followed the rules of logic, everything that followed would be unquestionably true as well. This idea was intoxicating. But it suggested that knowledge could be perfect, that doubt could be eliminated, that humans with enough care could build a fortress of certainty. But here is the thing about axioms. They are not proven, they are chosen. Euclid picked statements that felt obvious, and they were. At least they felt obvious at the time. But feeling obvious is not the same as being unbreakable. As long as everyone agreed on the axioms, the system held. But the moment someone asked why those axioms and not others, the ground shifted. Euclid's system worked so well that nobody questioned it for a very long time. Which is ironic, because the entire system depended on not questioning the starting point. This created a new standard for truth. Not this works, not this feels right, but this follows logically. And once that standard exists, it applies to everything, including the axioms themselves. Euclid had created a machine that could not justify its own foundation, and as math expanded, this became harder to ignore. People began to notice that some of Euclid's axioms were doing more work than they seemed, especially one, the parallel postulate, the one about lines never meeting. It looked harmless, but it was suspiciously complicated compared to the others. Centuries of mathematicians tried to prove it from the remaining axioms. They failed, over and over again. Eventually, they discovered something unsettling. You could remove it and replace it, and geometry would still work, just differently. This was the birth of non-Euclidean geometry, and with it came a terrifying realization. If you can change the axioms and still get a consistent system, then axioms are not self-evident truths. They are assumptions, carefully chosen assumptions, but assumptions nonetheless. This was not a small crack. This was a fracture, because once axioms are optional, certainty becomes conditional. Truth becomes relative to the rules you start with. And math, which had felt like the ultimate source of absolute truth, suddenly looked negotiable. Euclid had not broken math, but he had shown how fragile its foundation could be by demanding rigor. He had exposed the cost of rigor. Everything had to be justified, and if something could not be justified, it had to be assumed. This is where mathematicians began to feel uneasy, because assumptions are uncomfortable. They are promises without proof. And if math was going to claim absolute certainty, it needed to be honest about what it was assuming. So the community leaned harder into rigor. They demanded clearer definitions, stricter proofs, fewer leaps of intuition. They trusted logic more and feelings less, which sounds sensible, and it is. But it also creates a trap, because logic does not care how small or obvious something is. Once you commit to this path, everything must be accounted for, even the things you thought were safe. Even 1 plus 1, especially 1 plus 1. Euclid did not intend this. He was trying to make math secure. Instead, he made mathematicians paranoid, a healthy, productive paranoia, but paranoia nonetheless. And from this point on, common sense was no longer enough. Truth had to be earned, line by line, step by step, no shortcuts. The system demanded it, and once the system exists, you cannot selectively ignore it. If you want certainty, you have to pay the price, and the price is that even the most obvious truths are no longer free. They must be proven, or admitted as assumptions, and mathematicians, as we will soon see, are very bad at leaving things unproven. So while Euclid thought he was building a solid foundation, he had actually lit a very slow fuse, a fuse that would burn for centuries. And at the end of that fuse would be a book, 3 volumes thick, where someone finally triumphantly proved that 1 plus 1 equals 2. But first, math had to learn an uncomfortable lesson. That obvious is not the same as certain, and once that lesson is learned, there is no going back. There is a moment in every human system when trust quietly expires. It doesn't happen with a bang, it happens with a raised eyebrow. At first, everyone agrees on what feels obvious. The sun rises, fire burns, 1 plus 1 equals 2. And for a very long time, that is enough. But once math adopted Euclid's way of thinking, once it committed to building truth from carefully chosen starting points, obvious stopped being a compliment. It became a warning sign. Because obvious things are rarely examined, and unexamined things have a habit of hiding problems. Mathematicians started noticing that intuition could be unreliable, very unreliable. For centuries, people believed that heavier objects fall faster than lighter ones. It felt obvious. You drop a rock and a feather, and the rock wins every time. Case closed. Except it wasn't. When Galileo bothered to think about it carefully, and later test it properly, the intuition collapsed. The obvious thing was wrong, and this pattern repeated itself. The Earth felt stationary, time felt absolute, space felt flat. All of these things were obvious. All of them turned out to be incomplete or wrong, or at least more complicated than anyone expected. Math watched this unfold and grew nervous. If physics could betray intuition, why not numbers? If geometry could survive multiple axiom systems, why not arithmetic? The more math succeeded, the more dangerous assumptions became. Because once you rely on a result and build on top of it, a mistake at the bottom becomes catastrophic. A tiny crack in the foundation turns into a collapsing tower. So mathematicians began to distrust anything that relied too heavily on "it just makes sense." They wanted arguments that could survive skepticism. Arguments that would convince someone who was actively trying to be difficult, especially someone who enjoyed being difficult, and mathematicians, historically, are very good at that. This is where paranoia enters the room, not the loud, frantic kind, the quiet, methodical kind, the kind that says, "Yes, I know this works, but can we prove it anyway?" This paranoia did not come from confusion. It came from success. Math had grown too powerful to be sloppy. Once you start describing reality with equations, once bridges stand or fall based on calculations, once navigation, astronomy, and engineering depend on numbers behaving perfectly, you lose the luxury of hand-waving. So standards rose, proofs became longer, definitions became sharper, language became more precise. Things that were once accepted without question were suddenly expected to justify themselves. And this is where 1 plus 1 began to look suspicious. Not because it was wrong, but because nobody had ever really asked it to explain itself. Addition was used constantly, but its foundation was informal. Everyone agreed on how to use it. But agreement is not proof. You can all agree on something and still be wrong. History is full of examples. So mathematicians asked uncomfortable questions. What does plus actually mean? What exactly is being added? What rules govern this operation? If you strip away apples and stones, what remains? The answer at first was not reassuring. Addition had been defined in terms of numbers, and numbers had been defined in terms of intuition, and intuition had been defined in terms of experience. This was a loop, a friendly loop, A useful loop, but a loop nonetheless. And loops are dangerous in logic. Logic likes straight lines. It wants definitions that go one way. If A depends on B, B should not secretly depend on A. And yet, arithmetic was full of these circular comforts. 1 plus 1 equals 2, because that's how counting works. Counting works because 1 plus 1 equals 2. Perfectly fine in daily life. Unacceptable if you are trying to build an unbreakable system. So mathematicians began to say things that sounded ridiculous to everyone else. They said things like, we need to define numbers before we can add them, which immediately raised another problem. Define numbers using what? More numbers? That would not help. You need something simpler, something more primitive, something that does not rely on arithmetic at all. This is where logic steps forward. Logic does not talk about numbers. It talks about relationships. If this, then that. All of these have something in common. None of these belong here. Logic felt safer. It felt less tied to intuition, more mechanical. And once logic entered the picture, the mood changed. Math stopped being comfortable. It became precise, formal, cold in a reassuring way. No leaps, no guessing, no you know what I mean. Just rules. This had consequences. Once logic became the standard, everything had to comply. You could no longer say this is true because it's obvious. You had to say, this is true because it follows from these definitions, which follow from these axioms which we have agreed to accept. And if you could not do that, your statement was not false. It was worse. It was unproven, which, in math, is a kind of limbo. Not wrong, but not allowed. And 1 plus 1 sat awkwardly in that space. Everyone knew it was true. Nobody doubted it. But nobody had shown, in the new formal language, exactly why. It was like a law that everyone followed but nobody had written down, and that made some people deeply uncomfortable. Because if you are serious about rigor, you cannot make exceptions. You cannot say everything must be proven except this one thing. That defeats the purpose. So the pressure built, not to question 1 plus 1, but to justify it, to anchor it, to make it immune to doubt. And this is the moment where mathematics quietly crossed a line. It stopped being about results. It became about foundations. It became self-aware. Math began examining itself, asking whether its own tools were trustworthy, whether its own language was precise enough, whether its own starting points were strong enough to carry the weight placed upon them. And once you start down that path, there is no turning back, because now the question is not whether 1 plus 1 equals 2. The question is whether you know why. And knowing why, in this new world, means building the answer from the ground up. No sheep, no apples, no intuition, just logic. And patience. A lot of patience. Because the moment obvious stops being enough, even the simplest truths become projects. Long ones. And somewhere in the distance, still unseen, a very meticulous man is preparing to take this idea to its extreme. But before he arrives, math needs one more ingredient. Something that promises clarity. Something that promises order. Something that claims it can clean up thinking itself. Logic is about to stop being a background tool and start becoming the main character. Once you start paying attention to assumptions, you see them everywhere. They are quiet. They hide under statements that sound confident. They pretend to be facts. And math, for all its reputation of certainty, is built entirely on them. This is an uncomfortable realization, because assumptions are things you agree not to question. They are the ground rules of a game. You don't prove them. You accept them. And as long as everyone agrees, the game works. Euclid understood this, even if he didn't dwell on it. His axioms were not proven truths. They were starting points, statements chosen because they felt undeniable. But feels undeniable is not the same as cannot be denied. And once mathematicians noticed this, they started to worry. What if the entire structure of math was resting on ideas that only felt true because nobody had challenged them yet? This is where the house of cards metaphor becomes popular. Each theorem depends on previous theorems. Those depend on definitions. Definitions depend on axioms. And axioms depend on agreement. Pull out one card at the bottom, and the entire thing collapses. Now, to be fair, this does not mean math is fragile in practice. Bridges still stand. Calculations still work. Planes still land where they are supposed to. Reality is forgiving, but mathematicians are not trying to describe what usually happens. They are trying to describe what must happen, and must does not like ambiguity. So they began to examine their foundations with uncomfortable honesty. They asked questions like, why do we accept this axiom? What happens if we change it? Are there hidden assumptions we didn't notice? This was not a sign of weakness. It was a sign of maturity. Math had grown old enough to question its own childhood beliefs. But questioning foundations is exhausting, because you quickly realize how little is truly solid. Even logic, the thing meant to save everything, relies on rules you have to accept. Why does if A then B behave the way it does? Why do contradictions break everything? Why can't something be both true and false? These things feel obvious, which, again, is a red flag. The deeper mathematicians went, the more they noticed a pattern. Every system, no matter how careful, rests on something it cannot prove. There is always a starting point, always a place where you say, we stop asking questions here. And that realization is deeply unsatisfying if your goal is absolute certainty, because it means certainty is conditional. True if these assumptions hold. True if we accept these rules. True within this system. Not true in some cosmic, unquestionable sense. For most people, this is fine. For mathematicians obsessed with rigor, it is intolerable. They wanted something better. They wanted a foundation so clean, so transparent, that nothing suspicious could hide inside it. They wanted to reduce math to its simplest possible components. Not numbers, not shapes, not even equations. They wanted pure logic. Statements about statements. Rules about reasoning itself. The hope was simple. If you build math out of logic, and logic is undeniably valid, then math inherits that certainty. It is a beautiful idea, and a dangerous one, because now the entire weight of mathematics rests on the idea that logic itself is flawless, that its rules are beyond question, that its foundations are immune to the same doubts that haunted geometry and arithmetic. And this is where mathematicians start losing sleep, because logic feels solid, but so did Euclid's axioms, and so did common sense. The fear was not that math was wrong. The fear was that math might be less absolute than it claimed. And if that were true, then the dream of perfect certainty would be just that, a dream. So the pressure increased. Definitions became more careful. Proofs became more formal. Language became symbolic, precise, almost inhuman. Mathematics slowly drifted away from intuition and toward formal systems. Systems where everything was explicit. Nothing was implied. Nothing was assumed without being clearly stated. This is the environment where foundational work thrives, and it is also the environment where simple ideas become unrecognizable, because when you strip something down far enough, it stops looking like itself. A number is no longer a quantity. It becomes a construct, a logical object defined by properties. And once you start defining things this way, you realize something unsettling. You can define many different systems, each internally consistent, each logically valid, each based on different assumptions, which means math is not a single monolith. It is a collection of worlds defined by their axioms, and truth exists inside those worlds, not above them. This is a difficult thing to accept, especially if you grew up believing that math was the ultimate authority, that it described reality in some perfect, unquestionable way. Instead, it turns out math is more like a language, extremely precise, extremely reliable, but still dependent on rules we choose. This does not make math weak. It makes it honest. But honesty can be unsettling. And for some mathematicians, this was not good enough. They did not want honesty. They wanted certainty. They wanted a system so tight that nothing could escape, so complete that no question could remain unanswered, so perfect that doubt would have nowhere to hide. And this desire, this very human desire for absolute security, is what sets the stage for what comes next. Because if you want to eliminate doubt, you need a tool that can inspect reasoning itself, a tool that can say not just what is true, but why it must be true. That tool is logic. Not logic as common sense. Not logic as that seems reasonable, but logic as mathematics. Logic as a formal system. logic as the ultimate foundation, and once logic steps into that role, everything changes, because now math is no longer just about numbers or shapes. It becomes about thought itself, about how conclusions follow from premises, about what it means to know something for sure. And that shift, quiet and subtle as it may seem, marks the beginning of a new era. An era where the goal is no longer solving problems. The goal is justifying existence. And in that world, even 1 plus 1 must stand trial, not because it is guilty, but because nothing is above suspicion. And now, finally, we are ready to meet logic in its full formal form, not as a helpful friend, but as the strict caretaker of truth, the kind that tidies up your thinking, whether you like it or not, the kind that does not laugh at jokes, and the kind that insists on seeing every step, no matter how obvious it feels. Logic has a reputation problem. Most people imagine it as cold, robotic, and deeply unimpressed by human feelings. Which is fair. Logic is not here to comfort you. It is here to correct you. But long before logic became symbols and formulas, it was simply an attempt to understand thinking itself. The earliest version of this came from Aristotle. Aristotle was interested in how conclusions follow from ideas, not what people believe, but how beliefs connect. He noticed something simple. If all humans are mortal, and Socrates is a human, then Socrates is mortal. You do not need to know anything about Socrates to accept this. You do not need to trust Aristotle. The structure does the work. This was powerful. It suggested that reasoning could be studied independently of content, that thinking itself had rules, and if you followed those rules, you would not accidentally think nonsense. This idea was incredibly appealing to mathematicians, because math is not about opinions. It is about consequences. If you accept these premises, you must accept this conclusion. Logic promised a way to guarantee that, to separate valid reasoning from sloppy reasoning, to clean up thought, which is why logic slowly became math's favourite tool. Think of logic as a very patient friend, the kind who listens to your entire argument, nodding quietly, and then says calmly, "That doesn't follow," not angrily, not dramatically, just with a gentle disappointment that somehow hurts more. Logic does not argue about whether something feels true. It asks whether it follows from what came before, and if it doesn't, the conversation ends. This was exactly what mathematicians wanted. No appeals to intuition, no appeals to authority, no appeals to tradition, just structure. So over time, logic became more formal. People began writing down explicit rules. If a statement is true, then certain other statements must also be true. If a statement is false, then something else happens. These rules were meant to be mechanical, so clear that even a machine could follow them. And once you have mechanical rules, you have something beautiful. You have predictability. Logic does not get tired. It does not get emotional. It does not make exceptions, which makes it perfect for foundations. At least that was the hope. Because if math could be built on logic, and logic was unquestionably valid, then math could inherit that unquestionable certainty. It was like putting your house on bedrock instead of soil. But here is the thing about logic. It feels obvious, which, as we have learned, is suspicious. Why should these rules work? Why should contradictions destroy everything? Why should if A then B behave the way it does? These rules feel inevitable because our brains evolved to think this way, but evolution is not a proof. Still, logic worked incredibly well. It allowed mathematicians to formalize arguments that had previously relied on intuition. It allowed them to catch subtle mistakes. It allowed them to say not just this is true, but this must be true, given these premises. And gradually, math became more symbolic. Words were replaced with symbols. Sentences were replaced with formulas. Not because mathematicians wanted to be confusing, but because symbols are precise. They leave less room for interpretation, and interpretation is where errors hide. As logic took center stage, math began to change. Proofs became longer. Not because ideas became harder, but because nothing was allowed to be implicit. Every step had to be justified. Every move had to follow a rule. It was slow, painfully slow, but it was safe. And this is where things start to feel a little strange. Because once you insist on this level of precision, Even familiar ideas become unfamiliar. Addition is no longer something you do, it is something you define. A number is no longer something you count, it is something you construct. And logic, which was supposed to make everything clearer, starts to feel abstract, almost distant from reality. You are no longer thinking about apples. You are thinking about statements. Statements about sets, sets defined by other sets. It is all very clean and very removed. But mathematicians accepted this trade. They gave up intuition for certainty. They trusted that if logic was sound, the results would be too. And for a long time, this seemed to work. Math expanded rapidly. New fields emerged. New structures were built. And logic sat quietly underneath it all, doing its job. But there was a problem nobody wanted to look at too closely. Logic itself had rules, and those rules were assumed. They were not proven, which meant the foundation had simply moved. Instead of resting on intuition about numbers, math now rested on intuition about reasoning. This was better, but was it perfect? Some mathematicians were not satisfied. They noticed that even logic depended on things being well defined, that even formal systems could hide assumptions, and that even the cleanest rules could produce unexpected results. This is where the obsession begins. Because once you see that assumptions never truly disappear, you have two choices. You can accept it, or you can try to eliminate them anyway. Some mathematicians chose the second option. They believed that with enough care, enough precision, enough effort, it might be possible to create a system so complete that nothing would escape it. A system where every truth could be derived. A system where doubt would have nowhere to live. This dream had a name, the dream of absolute certainty, and it was about to collide with reality. But before it did, math would experience a period of intense optimism, a belief that everything could be organized, formalized, and secured, a belief that logic, properly applied, could tame even the wildest ideas. And it is in this optimistic moment that the stage is set for the great project. The project that would eventually produce a 360-page proof of something everyone already knew. But to understand why anyone thought this was a good idea, we need to look at the world math found itself in. A world changing faster than ever. A world full of new machines, new problems, and new anxieties. A world where certainty felt more important than ever. Which brings us to the panic of the 19th century. By the 19th century, mathematics was everywhere. It was in factories, in railways, in bridges and machines and maps. Numbers were no longer just counting sheep. They were moving people, moving goods, moving entire societies forward. This made math powerful, and power makes people nervous. The industrial world needed precision. If a calculation was wrong, a bridge collapsed. If a measurement was off, a train crashed. If an equation failed, a machine failed with it. There was no room for mostly correct. So mathematicians worked harder than ever to make things exact. They pushed deeper into analysis, algebra, and geometry. They explored infinity. They played with limits. They stretched old ideas into new shapes. And at first it was exhilarating. Everything seemed possible, until it wasn't. As mathematics grew more abstract, strange things started happening. Paradoxes appeared. Results that seemed logically correct, but deeply unsettling. Statements that could not be easily classified as true or false. Math was doing things it had never done before, and nobody liked it. One famous example involved infinity. Mathematicians began comparing infinite sets. They discovered that some infinities were bigger than others, which sounds like a joke until you realize it's not. You could match every whole number with an even number. 1 to 2, 2 to 4, 3 to 6. No leftovers, which means there are just as many even numbers as whole numbers. This was uncomfortable. Infinity was not behaving like a number. It was behaving like a trap. Then there were paradoxes involving sets. Sets that contained themselves, sets that didn't. Questions like, does the set of all sets that do not contain themselves contain itself? If it does, it shouldn't. If it doesn't, it should. Either way, logic breaks. These were not puzzles. They were warning signs. They showed that something deep in the foundations was unstable. The rules everyone trusted were producing contradictions, and in logic, contradictions are fatal. Once you allow a contradiction, anything becomes provable. True and false collapse into meaninglessness. This terrified mathematicians, not because they thought math was useless, but because they realized they didn't fully understand why it worked. For centuries, intuition and tradition had guided the way. Now those guides were failing, the old comfort was gone, and in its place was anxiety. A quiet, scholarly anxiety that manifested as long papers, heated debates, and very stern letters. The 19th century became a time of foundational crisis. Mathematicians began asking questions they had avoided for generations. What exactly is a number? What exactly is a set? What exactly counts as a valid proof? And most importantly, can math be made completely rigorous? Or is uncertainty unavoidable? This was not an academic concern. Math had become too important to leave shaky. Entire technologies depended on it. So a movement began. A movement toward formalism, toward making every assumption explicit, toward writing down not just results, but the rules for obtaining results. The idea was simple. If paradoxes come from hidden assumptions, then eliminate hidden assumptions. Put everything on the table. Define everything. Prove everything. Even the obvious things. Especially the obvious things. This is where the mood of mathematics shifts. It becomes self-conscious, careful, almost defensive. Mathematicians stop trusting intuition and start trusting symbols. They stop saying clearly and start saying by definition. The language becomes dry, precise, unforgiving, and this is also where mathematics becomes much harder to read. Not because the ideas are worse, but because nothing is allowed to be implicit. Every step is spelt out. Every leap is broken into smaller leaps. And this meticulous style creates a new kind of beauty. A beauty of certainty. A feeling that if you follow the rules carefully enough, nothing bad can happen. This is where optimism returns. The belief spreads that mathematics can be rebuilt on a perfectly solid foundation. That all the paradoxes are just growing pains. That with enough care, everything will make sense again. This belief was not naive. It was backed by real success. Formal systems were developed. Logic was refined. Set theory was formalized. The tools were there. All that remained was to put everything together, to show that mathematics in all its complexity could be derived from a small set of clear principles. This was the dream, and like all ambitious dreams, it attracted ambitious people, people who enjoyed thinking carefully, people who were not afraid of complexity, people who found comfort in precision. And among them was someone who took this dream very seriously, someone who believed that mathematics should be not just powerful, but absolutely certain, someone who would look at the foundations of arithmetic and say, calmly and confidently, we can do better. But before we meet him, there is one more thing to understand, because the panic of the 19th century was not just about paradoxes, it was about trust. Math had promised certainty, and for the first time that promise felt fragile. So mathematicians did what humans always do when something important feels fragile. They tightened their grip. They formalized. They defined. They tried to make uncertainty impossible. And in doing so, they set the stage for one of the most ambitious projects in the history of human thought. A project that would attempt to prove everything, starting from nothing, including the fact that 1 + 1 = 2. And that is where the dream of absolute certainty truly begins. There is a moment in every long relationship when you realize the other person is not quite who you thought they were. Mathematics had that moment with numbers. For a very long time, numbers behaved nicely. They lined up. They stayed positive. They counted things. They did exactly what you expected them to do. And then, slowly, they started acting strange. The first troublemakers were negative numbers. At first, they made no sense. How can you have less than nothing? You can't have -3 sheep. If you try, people get upset. So for centuries, negative numbers were treated with suspicion. They were used reluctantly, if at all. But they worked. They solved equations that otherwise had no solutions. They made bookkeeping easier. They showed up whether people liked them or not. So mathematicians accepted them, uneasily. Then came irrational numbers. Numbers that could not be written as fractions. Numbers that never ended. Never repeated. They went on forever. This was deeply unsettling. The ancient Greeks had believed that everything could be expressed as ratios, whole numbers divided by whole numbers. Nice. Clean. Understandable. Then someone proved that the square root of 2 could not be written that way. It was a betrayal, a crack in the world view. Numbers were no longer tidy. They were infinite processes. You could approximate them, but you could never fully capture them. And then came infinity itself. Infinity had always been there, lurking in the background, but now mathematicians started treating it seriously. They tried to use it, measure it, compare it. This did not go well. Infinity refused to behave like a number. You could add to it and get the same thing. You could subtract from it and get nonsense. You could divide by it and get 0, or maybe not, depending on how you felt that day. It was powerful and dangerous. Then there were imaginary numbers, numbers involving the square root of -1, which should not exist. And yet they worked beautifully. They solved real problems. They described electrical circuits, waves and rotations. They were imaginary only in name. At this point, numbers had completely escaped their original job description. They were no longer about counting objects. They were abstract entities with strange rules and surprising behavior, and every time mathematicians expanded the number system, they gained power, but they also gained risk, because each new kind of number raised new questions. What rules apply to these numbers? Do the old intuitions still hold? Does addition behave the same way? Does multiplication? Can you still trust 1 + 1 to mean what it used to mean? In most cases, the answer was yes, but the fact that the question had to be asked at all was unsettling. Because math was no longer a single unified thing, it was a patchwork of extensions, each one carefully defined. Each one internally consistent, but all of them dependent on definitions, and definitions depend on logic. This is where the foundation problem becomes impossible to ignore. If numbers can be so strange, so varied, so abstract, then you cannot rely on intuition to tell you what is allowed. You need rules, clear rules, rules that apply to all numbers, no matter how weird they get. And once you start demanding that level of clarity, you realize something uncomfortable. You cannot even explain what a number is without already using numbers, which is circular, and circles are bad. So mathematicians began looking for something more basic than numbers, something simpler, something that could serve as raw material. They turned to sets. A set is just a collection of things, any things. It doesn't care what the things are. This was promising. You could define numbers as collections. 1 could be a set with 1 element. 2 could be a set with 2 elements. This felt concrete, at least at first, but even sets started behaving badly. Once you allow any collection, you can form very strange sets, sets that contain other sets, sets that contain themselves, sets that lead to paradoxes. The more carefully mathematicians tried to define everything, the more traps they discovered. It was like trying to clean a house and finding a new mess under every rug. And this is where 1 + 1 quietly re-enters the story, because addition assumes structure. It assumes that combining things behaves predictably, but predictability depends on definitions, and definitions depend on foundations. If numbers are strange and sets are strange, and logic itself rests on assumptions, then nothing is truly automatic anymore. Not even addition, not even 1 + 1. Nobody thought 1 + 1 was wrong. That was not the fear. The fear was that it was ungrounded, that it worked because of habit, not because it had been justified from first principles. And once that fear exists, it demands resolution. You cannot unsee it. So mathematicians began a radical project. They decided to start from the very bottom, from nothing, not physical nothing, logical nothing, empty sets, pure logic. They would define numbers carefully, define operations carefully, define proofs carefully, and then, step by step, rebuild arithmetic, not to change it, not to improve it, but to justify it, to show beyond doubt that the familiar rules really do follow from the foundations. This is not something you do quickly. This is not something you do casually. This is something you do if you care deeply about certainty, and if you are willing to spend an enormous amount of time proving things nobody else feels need proving. This is the mindset that takes you from counting sheep to writing hundreds of pages about 1+1. It is not madness. It is commitment, and it is also a little bit obsessive, because once numbers stop behaving like friendly tools and start behaving like abstract creatures with their own rules, you cannot treat them casually anymore. You have to pin them down, define them, control them, or accept that certainty is gone. Some mathematicians chose acceptance, others chose control, and among those who chose control, one project stood above all others, a project that promised to put mathematics on an unshakable foundation, a project that would rebuild numbers from logic alone, a project that would eventually prove that 1+1=2. But before we get there, we need to understand the dream that motivated it. The dream that certainty could be absolute, that math could be complete, that nothing would ever again behave badly. A beautiful dream, a dangerous dream, and the next chapter is where that dream finally takes shape. At some point, mathematics stopped asking how to solve problems. It started asking whether it could ever be wrong. This was not a casual question. It was a late-night question, the kind that keeps you awake even when everything seems fine. Because by the late 19th and early 20th century, math was doing remarkably well. It was predicting planets, designing machines, explaining waves and heat and motion. From the outside it looked flawless, but on the inside, something felt off. There were paradoxes lurking in the background, definitions that felt circular, assumptions that had never been properly examined, and once mathematicians noticed this, they could not unnotice it. So a dream emerged, a bold, optimistic dream, the dream of absolute certainty. The idea was simple to state and incredibly difficult to achieve. What if mathematics could be rebuilt from the ground up? What if every statement could be derived from a small set of clear rules? What if there were no hidden assumptions, no intuitive leaps, no informal shortcuts, just logic? Pure, transparent, mechanical logic. In this dream, mathematics would be like a perfectly designed machine. You put axioms in at the top. You turn the crank. Truth comes out the bottom. And every truth would be guaranteed. Not by tradition, not by experience, but by structure. This dream had a name, formalism, and it attracted mathematicians who liked things clean, very clean. These were people who found comfort in definitions, people who enjoyed precision, people who did not mind spending years clarifying something everyone else already accepted. They believed that if math was going to claim universal validity, it needed a universal foundation, one that did not rely on human intuition, one that did not depend on cultural habits, one that would work even if humans disappeared tomorrow. Logic seemed like the perfect candidate. Logic did not care about numbers. It did not care about geometry. It cared about relationships between statements, and relationships, in theory, could be made perfectly explicit. The hope was that logic was self-evident in a way nothing else was, that its rules were unavoidable, that denying them would be incoherent. This gave mathematicians confidence. If they could express all of mathematics in logical terms, then the foundations would finally be secure. So the project began. Definitions were rewritten, proofs were formalized, informal reasoning was treated with suspicion. Everything had to be stated explicitly, even the things that felt silly to write down, especially those things, because obvious ideas were where mistakes like to hide. In this new world, nothing was allowed to just make sense. If you could not point to a rule that justified a step, the step was illegal. This was exhausting, but it was also thrilling. It felt like progress, like mathematics was growing up, leaving behind childhood shortcuts and embracing adulthood responsibility. And for a while it worked. Large areas of math were successfully formalized. Results became more reliable. Arguments became harder to misunderstand. The system felt stronger. This optimism reached its peak with the belief that mathematics could be made complete, that every true statement could in principle be proven within the system. No loose ends, no unanswered questions, no uncomfortable mysteries, just a finished, polished structure. This belief was not foolish. It was based on success. Every time a paradox appeared, mathematicians managed to refine definitions and make it go away. Every time something seemed unclear, they found a way to clarify it. So why not keep going? Why not finish the job? Why not remove doubt entirely? In this dream, proving 1 + 1 = 2 was not a joke. It was a necessity. Because if the foundation was perfect, everything resting on it would be perfect too. And arithmetic was too important to be left informal. Numbers were everywhere. If anything deserved a rigorous foundation, it was arithmetic. So the goal became clear. Define numbers using logic. Define addition using logic. Define equality using logic. And then show, step by careful step, that the familiar rules really do follow. No sheep, no apples, no intuition, just symbols and rules. This was not about distrust. It was about responsibility. Math had become too powerful to rely on unexamined beliefs. And this project attracted people with a particular temperament, people who enjoyed long arguments, people who liked precision more than speed, people who were not afraid of complexity. One of those people was Bertrand Russell. Russell believed deeply in clarity. He believed that many philosophical problems came from sloppy language, and he believed that logic could fix that. For him, formalizing mathematics was not just a technical project, it was a moral one. A way to eliminate confusion, a way to make knowledge honest. But before Russell could rebuild arithmetic, he needed help, because the project was enormous. It would require new definitions, new symbols, new ways of thinking. It would require turning mathematics into something almost unrecognizable, and it would take years, many years. This was not a side project. It was a life project, and it would produce a book so ambitious, so dense, and so meticulous that it would become legendary, a book that would attempt to prove everything, starting from nothing, including the most obvious fact of all, that 1 + 1 = 2. But before that book could exist, we need to meet the man behind it, not as a symbol, not as a logician, but as a human being with opinions, flaws, and an extraordinary tolerance for overthinking. And that is where we are going next, to meet Bertrand Russell, professional overthinker, and the perfect person for this impossible task. Bertrand Russell was not the kind of person who could ignore a problem. If something bothered him, even slightly, it stayed bothered. It paced around his mind. It tapped him on the shoulder. It refused to be quiet. This made him brilliant. It also made him exhausting. Russell was born into British aristocracy, which meant two things. He was surrounded by books, and he had a lot of time to think. As a child, he was lonely, shy, quiet, more interested in ideas than in people, which is often how this story goes. He found comfort in certainty, and math, at least on the surface, promised exactly that. Clear rules, clear answers, no ambiguity. For Russell, math was not just useful, it was safe. But even as a young man, he noticed something troubling. The certainty math promised was not as solid as it looked. There were gaps, assumptions hiding in the shadows, statements everyone accepted but nobody had justified, and Russell had a deep emotional allergy to that kind of thing. He believed that vagueness was a moral failure, that sloppy thinking caused real harm, that unclear ideas led to confusion, and confusion led to suffering. This might sound dramatic. It was. Russell was dramatic. He believed that if humanity could just think more clearly, many of its problems would disappear. This made him very popular at dinner parties. Russell was not only a mathematician, he was a philosopher, a public intellectual, a writer, an activist. He had strong opinions about politics, war, religion, marriage, and basically everything else. He was imprisoned for his pacifist views. He wrote essays criticizing religion. He argued publicly with other philosophers. He lived a life full of conflict. But through all of it, one theme remained constant: his obsession with clarity. He wanted ideas to mean what they claimed to mean. And if they didn't, he wanted to fix them. When Russell looked at mathematics, he saw something powerful but unfinished. A machine that worked astonishingly well, but whose inner workings were not fully understood. This bothered him deeply, because if math was going to serve as the foundation for science, and science was going to explain reality, then math had to be absolutely solid. No guesswork, no hand-waving, no it's obvious. So Russell turned to logic. He believed that logic was the key to everything, that if mathematics could be reduced to logic, then its foundations would finally be secure. This idea was not entirely new. Others had flirted with it, but Russell took it seriously, very seriously. He began studying symbolic logic with intensity. He wanted to express mathematical statements in purely logical terms. No numbers, no geometric intuition, just symbols and rules. This was slow work, painfully slow, but Russell had patience, and more importantly, he had a kind of stubbornness that borders on admiration. He was not interested in shortcuts, he was interested in correctness. And then something happened that almost derailed the entire project. Russell discovered a paradox, a logical contradiction hiding inside the very foundations of set theory, the kind of contradiction that destroys everything. It became known as Russell's paradox, the set of all sets that do not contain themselves. Does it contain itself or not? Either answer leads to a contradiction. This was catastrophic. If logic itself contained contradictions, then the dream of absolute certainty was in danger. Russell was horrified, but also energized, because finding a flaw meant it could be addressed. He didn't abandon the project. He doubled down. He worked obsessively to fix the foundations, to refine definitions, to eliminate contradictions. This is where Alfred North Whitehead enters the story. Whitehead was older, calmer, more patient, less interested in public controversy. He was a mathematician and philosopher with a taste for structure. Where Russell was fiery, Whitehead was steady. They complemented each other perfectly. Together, they decided to attempt something unprecedented. They would rebuild mathematics from the ground up. Using logic alone, they would define numbers, operations, and proofs in the most rigorous way possible. And they would write it all down. Everything. No matter how long it took. No matter how tedious it became. This was not a project designed for popularity. It was not designed for readability. It was designed for certainty. They knew it would be difficult. They knew it would take years. They probably did not fully appreciate just how massive it would become, but they believed it was necessary. Russell was driven by more than technical curiosity. He believed that clarity in mathematics could inspire clarity in thought, that if people learned to reason properly, the world might become more rational, more peaceful, less chaotic. This is a heavy burden to place on a math book, but Russell was not known for modest ambitions. So he and Whitehead began writing, line by line, definition by definition, symbol by symbol. They were not proving interesting theorems. They were proving that they were allowed to prove anything at all. This kind of work is invisible to most people. It lacks drama. It lacks payoff. It requires a tolerance for boredom that very few possess. Russell possessed it, in large quantities, and this is why he was the perfect person for this task. Not because he was the smartest, not because he was the most original, but because he was unwilling to accept uncertainty, because he could not let go of a problem once he saw it, because he believed that even the simplest truths deserved justification, especially the simplest truths. And this belief would lead him to one of the most ambitious books ever written, a book that would attempt to prove all of mathematics, from logic, from nothing, including the fact that 1 + 1 = 2. But before that proof could appear, before the famous page could be reached, Russell and Whitehead had to build something extraordinary, a book so dense that it nearly defeated its authors, a book so meticulous that it redefined what rigor meant, a book that would become both legendary and infamous, the book that nearly killed its authors. And that is where we are going next. Writing a book is hard. Writing a book that tries to prove all of mathematics from scratch is something else entirely. Bertrand Russell and Alfred North Whitehead did not sit down to write a normal book. They did not outline chapters about interesting results. They did not worry about pacing, readability, or whether anyone would enjoy it. They were not thinking about an audience. They were thinking about certainty. And certainty does not care if you are bored. The book they set out to write was called Principia Mathematica. The name alone is a warning. This is not a book you read casually. This is not a book you flip through before bed unless your goal is immediate unconsciousness. It is 3 volumes long, thousands of pages, dense with symbols, sparse with explanation, and absolutely relentless. Russell and Whitehead were not trying to impress anyone, they were trying to be correct, which meant everything had to be explicit. Every assumption had to be stated, every rule had to be written down, every step had to follow mechanically from the previous one. Nothing could be left to intuition. Nothing could be assumed just because it felt obvious. This makes for slow writing. Very slow writing. Imagine trying to explain a simple idea, but being forbidden from using any words that depend on that idea. You want to talk about numbers, but numbers are not allowed yet. You want to talk about addition, but addition does not exist yet. You want to say 1, but 1 is something you have to define later. So you start with logic. Pure logic. Statements, symbols, rules for manipulating those symbols. It is like building a city starting with individual bricks. You cannot talk about houses yet. You cannot talk about streets. You are still arguing about what counts as a brick. This was the level they worked at. Page after page of careful definitions. Not exciting definitions. Not clever definitions. Definitions that exist solely to prevent misunderstandings. Russell once joked that it took them several hundred pages to prove that 1 + 1 = 2. This was not a joke meant to be funny. It was a warning, because what they were really proving was not arithmetic. They were proving that arithmetic was allowed. They were showing that the familiar rules of numbers could be derived from logic without contradiction. This required extraordinary patience, and it took a toll. Russell later described the experience as exhausting. Years of work, endless revisions, arguments over symbols and phrasing, moments where they realized that something they had assumed was not justified and had to be rebuilt. This kind of work does not provide quick rewards. There are no breakthroughs, no moments of sudden insight, just slow, grinding progress, and it nearly broke them. Whitehead was older and more measured, but even he felt the strain. Russell, with his restless mind and emotional intensity, struggled. There were moments where the project seemed impossible, moments where paradoxes threatened to reappear, moments where entire sections had to be rewritten because of a small oversight. This is the dark side of rigor. When you commit to absolute precision, mistakes become catastrophic. A single unclear definition can poison everything that follows, so the authors had to be merciless. Not just with the material, but with themselves. They questioned every step, every symbol, every assumption, and the result was a book that very few people could read. Not because it was badly written, but because it demanded total attention. Principia Mathematica does not meet you halfway. It expects you to meet it fully prepared, which almost nobody was. When the book was finally published, it was admired, respected, and quietly avoided. Mathematicians recognized its importance, but they also recognized its difficulty. It was not a textbook. It was not a reference. It was a monument, a demonstration of what was possible if you were willing to pay the price, and that price was accessibility. The book was so formal, so stripped of intuition, that even experienced mathematicians found it exhausting. Reading it felt less like learning and more like endurance. But that was the point. Principia Mathematica was not meant to teach. It was meant to justify, to show that mathematics could, in principle, be built on logic alone. And in doing so, it redefined rigor. After Principia, standards changed. Mathematicians became more careful, more explicit, more precise. Even those who never read the book felt its influence. But buried deep inside this enormous work, something remarkable happened. After hundreds of pages, after endless definitions, after constructing numbers from logical primitives, after defining addition in the most careful way imaginable, Russell and Whitehead reached a result, a small result, a modest result, one that everyone already believed. They proved that 1 + 1 = 2. It did not look impressive. There was no fanfare, no dramatic conclusion, just a line in a sea of symbols. But that line represented years of work, and it represented the fulfillment of a promise. The promise that arithmetic was not just intuitive, it was logically grounded, at least within the system they had built. And yet, even as they achieved this milestone, something was off. The proof did not feel satisfying, not in the way a beautiful theorem does. It felt anticlimactic. Like finishing a marathon and realizing the finish line was exactly where you expected it to be. The achievement was not the result. It was the journey. The fact that it could be done at all. That such a basic truth could be traced back to logic without contradiction. This was the triumph of Principia Mathematica. Not that it taught anyone new math, but that it demonstrated the extreme limits of rigour. It showed how far you could go if you insisted on absolute clarity. And it also showed how much effort that clarity required. The book nearly killed its authors, not because it was wrong, but because it was uncompromising. It demanded perfection, and perfection is exhausting. Still, for a moment, it seemed like the dream had been realised. Mathematics had been placed on a firm foundation. The paradoxes had been addressed. Arithmetic had been justified. Everything appeared to be in order. The house of cards had been replaced with something sturdier, or so it seemed, because even as Principia Mathematica was being celebrated, something else was happening. Something quiet, something unexpected. A young mathematician was preparing to show that the dream of absolute certainty had limits, that no system, no matter how careful, could prove everything, that some truths would always lie beyond reach, and that discovery would change everything. But before we reach that twist, there is still work to be done, because proving 1 + 1 = 2 was not the end of the story, it was just the most famous example. To understand why it took so long and why it mattered at all, we need to look more closely at how numbers were actually built. From nothing, slowly, carefully, one definition at a time. And that is where we are going next, to the strange process of building numbers from nothing at all. At this point in the story, it helps to forget everything you know about numbers. This is not easy. Numbers are stubborn. They follow you around. They sneak into your thoughts. They sit quietly in the background, pretending to be obvious. So for the next little while, imagine that numbers do not exist. Not 1, not 2, not even 0. All you are allowed to use is logic. Statements, rules about statements, and one very strange idea, the empty set. The empty set is exactly what it sounds like. It is a collection that contains nothing, no objects, no elements, no surprises. It is nothing, but carefully defined. And this is where Russell and Whitehead begin. Not with 1, not with counting, but with nothing. This is already a warning sign, because when mathematicians start from nothing, they usually mean business. The empty set is useful because it does not rely on intuition. It does not depend on physical objects. It is defined purely by a property. There is nothing in it. That is all. From this, they begin to build, very slowly, very carefully. The number 1 is defined as a set containing exactly one element, but since we do not have numbers yet, that element has to be something else. So they choose the empty set. 1 is defined as the set that contains the empty set. That is it. 1 equals the set whose only member is the empty set. This is not meant to be intuitive. It is meant to be precise. The number 2 is defined as the set that contains 2 elements. Which 2? The empty set and the set containing the empty set. In other words, 2 is the set that contains 0 and 1. 3 is the set that contains 0, 1, and 2, and so on. Each number is defined in terms of the ones that came before it. This creates a ladder. Each step depends on the previous step. Nothing is assumed. Everything is constructed. This is how numbers are built from nothing. Not quickly, not elegantly, but carefully. At this point, most people feel a mild sense of discomfort, because this does not feel like what numbers are. And that is correct. This is not how humans normally think about numbers. This is how you think about numbers. If your goal is to remove ambiguity, if you want to make sure that when you say 2, everyone agrees on exactly what you mean, not emotionally, not intuitively, but structurally, once numbers are defined this way, operations can be defined too. Addition becomes a rule for combining these sets, not by intuition, not by counting apples, but by formal procedures that manipulate the underlying structures. This is where the pages start to pile up, because every rule needs to be justified, every property needs to be proven. You cannot assume that adding 1 to a number behaves the way you expect. You have to show it, and showing it means working through definitions, slowly, line by line, symbol by symbol. This is why proving 1 plus 1 equals 2 takes so long. You are not proving a fact about apples. You are proving a fact about abstract objects built from nothing. Objects defined entirely in terms of logic and sets. By the time you reach the statement 1 plus 1 equals 2, you have already done an enormous amount of work. You have defined what 1 is, what 2 is, what plus means, what equals means, and you have shown that these definitions behave consistently. Only then are you allowed to write down the familiar equation, and when you do, it looks strangely unimpressive, a small result at the end of a very long road. This process reveals something important. The difficulty is not in the statement. The difficulty is in the standards. If you demand that everything be justified from nothing, nothing is easy. Even the simplest truths become labor-intensive. This is not because math is broken. It is because the goal has changed. The goal is no longer to calculate. It is to justify, and justification is expensive. Building numbers this way also reveals something else. Numbers are not primitive. They are constructed. They are the result of definitions and agreements. This does not make them arbitrary. It makes them precise. It shows that the familiar properties of numbers are not magical. They are consequences. Consequences of choices made at the foundation. This is both reassuring and unsettling. Reassuring because it shows that arithmetic is not mysterious. Unsettling because it shows that it depends on a framework. Change the framework and the results might change too. This is why Russell and Whitehead were so careful. They wanted a framework that felt inevitable, one that did not smuggle in hidden assumptions, one that made the familiar rules unavoidable. And to their credit, they succeeded. Within their system, arithmetic behaves exactly as expected. 1 plus 1 equals 2. 2 plus 2 equals 4. Everything works. But the cost is visibility. The connection to everyday experience is gone. Numbers no longer feel like quantities. They feel like objects in a logical game, which is fine, as long as the game is consistent. And that consistency is what Principia Mathematica aimed to demonstrate. So when people laugh about the 360-page proof, they are laughing at the wrong thing. The proof is not ridiculous. It is honest. It shows what happens when you refuse to take shortcuts. When you refuse to say this is obvious. When you insist on knowing exactly why something works. This is not how math is done day to day. And it does not need to be. Most mathematicians are happy to rely on established foundations. They do not rebuild arithmetic every morning. But once, at least once, someone had to check. Someone had to make sure the ladder was solid. And that is what this chapter of the story is about. Not the number 1, not the number 2, but the commitment to certainty. The willingness to start from nothing and build patiently upward, one definition at a time. Even if it takes hundreds of pages. Even if the result feels anticlimactic. Because sometimes knowing that something works is not enough. Sometimes you want to know why. And once you start asking that question, there is no such thing as an easy answer. But now that the numbers exist, and addition exists, and equality exists, we can finally approach the moment everyone has been waiting for. The page where 1 plus 1 becomes 2. Not emotionally, not intuitively, but formally. And that moment, surprisingly, is both impressive and deeply underwhelming, which makes it perfect for the next chapter. At this point in the story, it is very tempting to laugh. 360 pages to prove something a child knows before breakfast. It sounds absurd. It sounds like the kind of thing mathematicians would joke about to scare normal people away. And to be fair, it does sound ridiculous. So let's address the obvious reaction. Was this a waste of time? Were Russell and Whitehead just overthinking things? Were they trapped in an intellectual spiral, unable to let go of something simple? The answer is no. But also, kind of yes. And that tension is the entire point. From the outside, the proof looks pointless. Nobody needed convincing that 1 plus 1 equals 2. Civilizations were not collapsing due to uncertainty about addition. The world was functioning just fine. So why bother? Because the proof was never really about the result. It was about the foundation. Russell and Whitehead were not trying to teach anyone arithmetic. They were trying to answer a different question entirely. Can mathematics justify itself? Can it explain why its rules work? without appealing to intuition, experience, or common sense. If the answer was yes, then math could claim a special kind of authority, not just usefulness, not just reliability, but inevitability. This mattered deeply to people who saw mathematics as the backbone of knowledge. If science rests on math, and math rests on assumptions nobody has checked, then everything above it feels a little less secure. Russell did not like that feeling, so he did what he always did when something bothered him. He stared at it until it either made sense or broke. The 360-page proof is what happens when you refuse to stop asking why, not because the question is practical, but because the question exists. This kind of thinking is not efficient. It is thorough, and there is a difference. Efficiency is about speed. Thoroughness is about coverage. Russell and Whitehead wanted to make sure there were no hidden traps, no silent assumptions, no unexamined steps. They wanted to know exactly what was being used, and where. This is not how most mathematics is done, and it shouldn't be. If every calculation required rebuilding arithmetic from scratch, nothing would ever get finished. Math relies on trust. Trust in established results. Trust in shared definitions. Trust that someone somewhere has checked the foundations. Principia Mathematica was that check. Once. For everyone. Another misunderstanding is that Russell and Whitehead were trying to show how math should always be done. They weren't. They were showing that it could be done, that there existed at least one path from logic to arithmetic without contradiction. That was enough. Once that path existed, mathematicians could relax. They did not need to walk it again. They just needed to know it was there. This is like checking the structural integrity of a bridge. You don't rebuild the bridge every time you cross it. You just want to know that someone has checked the supports. So when people mock the 360-page proof, they are missing the point. The length is not a flaw. It is evidence of honesty. It shows what happens when you refuse to compress ideas into intuition, when you expand every step until nothing is hidden. Of course it takes a long time. Of course it feels excessive. Excess is the price of transparency. There is also something quietly admirable about the effort. It is a refusal to be satisfied with good enough, a commitment to understanding rather than convenience. That kind of thinking has driven a lot of human progress, not because it is practical in the moment, but because it changes how we think about knowledge. At the same time, it is important to admit that this approach has limits. The proof is not beautiful. It is not enlightening in the way a clever insight can be. It does not make you see addition in a new light. It justifies it, which is a different kind of achievement. Some mathematicians found Principia inspiring. Others found it unbearable. Many respected it without loving it. And that is okay. Not every important thing is enjoyable. Some things are important because they exist, not because they are pleasant. There is also a deeper lesson hiding here, one that goes beyond math. The story of the 360-page proof is a story about human standards, about what we consider acceptable. At some point, it works, stopped being enough. At some point, everyone agrees, stopped being enough. Math raised the bar, and once the bar is raised, you cannot lower it without feeling dishonest. Russell did not invent this pressure. He responded to it. He lived in a time when certainty felt fragile, when systems were growing larger and more complex, when mistakes carried real consequences. In that context, overthinking is not madness. It is caution, and caution, when taken seriously enough, turns into rigor. The irony is that this level of rigor is almost never required in daily life. You do not need to justify arithmetic to make dinner. You do not need set theory to balance a budget. You do not need logic symbols to count sheep, and Russell knew this. He was not confused about practicality. He was obsessed with foundations, with what lies underneath everything else. That obsession produced something extreme, but it also produced clarity. Principia Mathematica showed exactly how much work is hidden inside obvious ideas. It revealed the invisible structure supporting everyday reasoning, and once you see that structure, you cannot pretend it isn't there. This does not mean everyone should care. Most people don't. Most people shouldn't. But someone had to care. Someone had to ask the uncomfortable questions. Someone had to do the slow, thankless work of justification. And that someone was Russell, with help from Whitehead. So no, It wasn't stupid. It was uncompromising. It was excessive. It was deeply human. And in a strange way, it was humble, because it admitted that even the simplest truths deserve explanation. That certainty is not something you assume. It is something you build, carefully, patiently, page by page. And now that the work has been done, now that the definitions are in place, now that the logical machinery is humming quietly in the background, we can finally arrive at the moment everyone has been waiting for. The moment when all of this effort produces its most famous result. The page where 1 plus 1 finally becomes 2. Not with a bang, not with celebration, but with a line of symbols that quietly says, yes, this is allowed. And that moment, understated and oddly boring, is exactly what makes it so perfect. Which brings us to the most anticlimactic climax in mathematical history. After all that work, the moment itself is almost disappointing. There is no drum roll, no dramatic reveal, no sense that history is being made. Just a page, some symbols, a line that quietly states a result everyone already expected. This is where 1 plus 1 equals 2, and if you were hoping for fireworks, you will not find them. The famous proof appears deep inside Principia Mathematica, long after most readers have surrendered. It is not framed as a revelation. It is not even highlighted. It is simply another consequence of definitions and rules, which is exactly the point. By the time Russell and Whitehead arrive at this statement, the real work is already done. The definitions exist. The logical machinery is in place. Numbers have been constructed. Addition has been defined. Equality has been formalized. At this stage, 1 plus 1 equals 2 is no longer surprising. It is inevitable. That is the goal. The proof itself is not elegant. It is not memorable. It is not something you would put on a poster. It is a technical confirmation that the system behaves as intended. And that is why it matters. Because it shows that the familiar rules of arithmetic are not assumptions. They are consequences. Within this framework, 1 plus 1 cannot equal anything else. It must equal 2, not because it feels right, but because the structure demands it. This is what Russell and Whitehead wanted. Not emotional satisfaction, not intuitive comfort, logical necessity. From a distance, this feels like a strange victory. You spend years building a massive logical structure. You fight paradoxes. You define everything carefully. And at the end, you arrive at the same place everyone else started. It feels anticlimactic. But this anticlimax is intentional. It means the system is working. If the conclusion had been surprising, something would have gone wrong. The beauty of this moment is not in what it says, it is in how quietly it says it. No excitement, no hesitation, just a calm statement that follows naturally from everything that came before. It is like reaching the top of a mountain and realizing the view looks exactly like the map promised. Slightly underwhelming, deeply reassuring. This is also where many people misunderstand the story. They imagine Russell and Whitehead sitting triumphantly, celebrating the moment. That is unlikely. They probably felt relief and exhaustion, because proving 1 plus 1 equals 2 was not the goal. It was a checkpoint, a confirmation that the foundations were holding, that the definitions had not secretly broken something, that the logical engine was producing the expected output. In that sense, the proof is like a test case. You do not write a program to celebrate that it prints "Hello World." You write it to make sure the system works. Once it does, you move on. And Russell and Whitehead did move on. They continued formalizing mathematics. They continued refining logic. They continued believing, at least for a while, that the dream of absolute certainty was within reach. But for the rest of the world, this page became symbolic. It became shorthand for overthinking, for excessive rigor, for the lengths mathematicians will go to avoid assuming anything, and that reputation is not entirely unfair. The proof is excessive. It is deliberately excessive. It shows what happens when you refuse to trust intuition, when you insist on seeing every step, no matter how small. Most of the time this is unnecessary, but sometimes it reveals something important. In this case, it revealed that arithmetic rests on a foundation of logic and definitions, not on common sense, not on experience. And that distinction matters, because it means arithmetic is not just something that happens to work in our world. It is something that works within a formal system. That system can be examined, modified, compared to others. This perspective changed how mathematicians thought about their work. Math was no longer just a collection of truths. It was a collection of structures, each with its own rules, each with its own consequences, and truth became relative to structure. This is a subtle shift, but a profound one. The page where 1 + 1 = 2 marks the moment when arithmetic officially joins this formal world, where it becomes something that can be derived rather than assumed. For many mathematicians, this was enough. They accepted that the foundations had been checked. They moved on to more interesting problems. Principia Mathematica did not become a daily reference. It became a historical anchor, something you respected without revisiting. But there was an irony hiding in this triumph, because even as Russell and Whitehead completed their proof, the dream that motivated it was already in danger. The dream of absolute certainty, the belief that all of mathematics could be captured within a single, complete, consistent system. That belief was about to be challenged, not by intuition, not by experience, but by logic itself, which is the most dramatic twist possible in a story like this, because the tool meant to save everything was about to reveal its own limits. And when that happened, the meaning of the 360-page proof would change. It would still be impressive, still important, but no longer sufficient. The page where 1 + 1 = 2 would stand as both a triumph and a warning, a triumph of rigor, a warning about ambition, because if even logic has limits, then certainty might always be conditional, and that realization would reshape mathematics forever. But before we face that twist, it is worth sitting with this moment a little longer, with the quiet satisfaction of a system behaving as expected, with the idea that sometimes doing something the hard way is not about the result. It is about knowing that the result is justified, that when you say 1 + 1 = 2, you are not relying on habit or trust. You are relying on a carefully constructed framework. That knowledge does not change how you count. It does not change how the world works, but it changes how you think about thinking. And that is the deeper legacy of this page, not the equation, but the attitude behind it, an attitude that says nothing is above examination, that even the simplest truths deserve explanation. That certainty is not free, it is built, and once built, it allows you to rest, which is fitting, because after all this effort, after all these pages, after all this careful reasoning, the conclusion is exactly what you expected. 1 + 1 = 2. And now that we have arrived there, we can finally turn our attention to the twist. The moment when mathematics discovers that even the most careful systems cannot capture everything, that there are truths that cannot be proven, that the dream of absolute certainty has boundaries, and that discovery belongs to someone else entirely, a quiet figure, working alone, about to change everything. Which brings us to the irony that no amount of rigor could avoid. The realization that even after proving 1 + 1 = 2, mathematics still was not finished. Not even close. For a brief moment, it felt like mathematics could relax. The foundations had been examined. The paradoxes had been addressed. Arithmetic had been rebuilt from logic. 1 + 1 = 2. What more could you want? As it turns out, quite a lot. Because while Russell and Whitehead were finishing Principia Mathematica, a quiet shift was already underway. A shift that would undermine the very dream their work was built on. The dream of absolute certainty. The belief that mathematics could be complete. That every true statement could in principle be proven from a fixed set of rules. This belief was not arrogant. It was optimistic. And optimism has a way of attracting surprises. Enter Kurt Gödel. Gödel did not look like a revolutionary. He was quiet, reserved, intensely focused. He did not argue loudly. He did not seek attention. He simply thought very carefully. And what he discovered was devastating. Gödel showed that any sufficiently powerful logical system has limits. Not practical limits. Logical limits. He proved that in any system capable of doing basic arithmetic, there will always be true statements that cannot be proven within that system, no matter how careful the definitions, no matter how rigorous the rules, no matter how many pages you write. There will always be statements that are true but unprovable. This result is known as Gödel's incompleteness theorem, and it is one of the most unsettling discoveries in the history of mathematics. because it means the dream of absolute certainty is impossible, not because humans are flawed, not because the system is sloppy, but because the system is powerful. The very strength of mathematics guarantees its incompleteness. Gödel's proof is subtle. It does not attack logic from the outside. It uses logic against itself. It constructs a statement that essentially says, this statement cannot be proven within this system. If the system proves it, the system is inconsistent. If the system cannot prove it, then the statement is true but unprovable. Either way, completeness is lost. This is not a technical inconvenience. It is a fundamental boundary. No amount of refinement can remove it. No clever definitions can escape it. Gödel showed that mathematics can never be both complete and consistent. You can have one, but not both. This hit the mathematical community like a quiet earthquake. There was no explosion, no collapse, just a slow realization that something deeply hoped for was unattainable. The fortress of certainty had a horizon. There were things beyond it, and no bridge could be built. This does not mean that mathematics is unreliable. On the contrary, it is remarkably reliable. It means that certainty has limits, that there will always be truths that lie just beyond formal reach, statements that are meaningful, correct, and unprovable. This is where the irony becomes almost poetic. After all that effort, after all those pages, after all that care, after proving 1 + 1 = 2, mathematics discovers that it can never prove everything. The foundations can be strengthened, clarified, examined, but they cannot be made complete. Russell was deeply affected by this. The project he had devoted years to was not invalidated, but its ultimate goal was shown to be unreachable. The dream of a perfectly closed system was over. And yet, something important had been learned. Gödel did not show that math was broken. He showed that math was alive, that it was rich enough to talk about itself, that it was powerful enough to generate truths that outgrew any single formal system. This is not a failure. It is a feature. It means mathematics is not a static monument. It is an evolving landscape, one where new truths appear, even as foundations remain solid. The proof that 1 + 1 = 2 still stands. It is still correct, still meaningful, still impressive, but it is no longer the final word. It is part of a larger story, a story where certainty exists but only within boundaries, where rigor is valuable but not omnipotent, where logic is essential but not all-powerful. This realization changes how you see the 360-page proof. It is no longer a step toward total certainty. It is a demonstration of how far rigor can take you, and also quietly where it must stop. Gödel did not undo Russell's work. He reframed it. He showed that no matter how carefully you build your system, there will always be truths that escape it. This is humbling and strangely comforting, because it means that mathematics, like human knowledge, is never finished. There will always be new questions, new boundaries, new ideas to explore. The dream of absolute certainty dissolves, but in its place appears something better, a recognition that knowledge can be strong without being complete. That understanding can be deep without being final, and that is where mathematics ends up, not as a perfect machine, but as a living structure, stable where it needs to be, open where it must be. The irony is that the very project meant to eliminate uncertainty ended up revealing its necessity, that even in the most rigorous systems there is room for mystery, and that mystery is not a flaw, it is an invitation to keep thinking, to keep exploring, to keep asking questions, even when the answers are not guaranteed. So yes, it took 360 pages to prove that 1 + 1 = 2, and even after that, mathematics was not complete. But that does not make the effort pointless. It makes it human, because the desire for certainty, even when it cannot be fully satisfied, drives us forward. It pushes us to understand more, to clarify more, to accept that some truths will always lie just beyond reach, and perhaps that is the real lesson. Not that everything can be proven, but that some things are worth examining anyway, even if in the end, certainty remains just slightly out of grasp. And now, having reached the limits of formal certainty, we can step back, away from symbols, away from proofs, and ask what all of this says about us. about human minds, about our need for reassurance, about why we overthink things, and why that overthinking is sometimes beautiful. Which brings us to the question that matters far beyond mathematics. What does all of this say about how humans think? And that is where we go next. By now it should be clear that this story is not really about math, or at least not only about math. It is about people, about how human brains behave when they encounter uncertainty. Because if you strip away the symbols, the books and the logic, what you are left with is a very familiar pattern. Something feels obvious. Someone asks why, and suddenly nothing feels simple anymore. This happens everywhere, not just in mathematics. We trust things because they work. We rely on habits because they are comfortable. We build routines, beliefs and systems that carry us through daily life. And most of the time, this is enough. But occasionally, someone comes along who cannot leave well enough alone. Someone who looks at a functioning system and says, quietly, I want to understand this more deeply. That impulse is neither practical nor efficient. It is psychological. It comes from a desire for security, from a need to know that the ground under your feet is solid. Bertrand Russell was not alone in this. He was just a particularly extreme example. Human brains crave certainty. We are pattern-seeking machines. We like predictability. We like knowing what will happen next. And when we cannot predict something, anxiety appears. Math, for a long time, felt like the antidote to that anxiety. It offered clear rules, clear answers, a sense that at least one part of the world was orderly. So when cracks appeared in the foundations of math, the reaction was emotional as well as intellectual. People felt uneasy. If even math has assumptions, what doesn't? This is why the project of formalization was so intense. It was not just about truth, it was about reassurance. Russell did not want math to be merely useful, he wanted it to be safe. And safety, in the human mind, often means certainty. But the brain has a strange relationship with certainty. It wants it, it depends on it, and it also has a habit of overdoing it. Once you start chasing certainty, it becomes tempting to demand more and more of it, to eliminate every possible doubt, to close every gap. This is where overthinking begins. Overthinking is what happens when the brain refuses to tolerate ambiguity. When it insists on answers even when the question is not strictly necessary. This is often framed as a flaw, and sometimes it is. Overthinking can lead to paralysis, to anxiety, to endless loops of questioning. But it can also lead to remarkable achievements. Science exists because people overthought everyday experiences. Philosophy exists because people overthought language. Mathematics exists because people overthought counting. The 360-page proof is an extreme example of this tendency. It is what happens when the desire for certainty is given unlimited time and intellectual tools. It shows both the power and the cost of that desire. The power is obvious. Clarity, precision, structures that can support enormous complexity. The cost is equally obvious. Distance from intuition, accessibility, human warmth. Principia Mathematica is not a friendly book. It is not meant to be. It is a monument to discipline, to restraint, to the refusal to assume. This reflects something deep about human cognition. We build mental shortcuts because we have to. The world is too complex to analyze from first principles all the time, so we trust, we generalize, we rely on intuition. And most of the time this works beautifully, but every now and then we stop and check. We slow down. We ask whether the shortcuts are still safe. This is healthy, but if you push it too far, you end up proving 1 + 1 = 2 over hundreds of pages, which is impressive, and also a little absurd. Gödel's discovery adds another layer to this psychological story. It shows that the desire for absolute certainty cannot be fully satisfied, that no matter how careful we are, there will always be limits. This is not just a fact about math. It is a fact about human knowledge. We can know a lot, we can justify a lot, but we cannot close the system completely. There will always be questions that cannot be answered from within, and this is where wisdom enters the picture. Wisdom is knowing when to stop, when to accept that something works well enough, when to trust without demanding absolute proof. Russell struggled with this. Many mathematicians did. Many humans do. The brain wants to keep digging, to keep questioning, to keep searching for firmer ground. Sometimes that search leads to insight. Sometimes it leads to exhaustion. The story of the 360-page proof sits right on that boundary. It is both a triumph of human reason and a cautionary tale. It shows what is possible when you refuse to accept ambiguity, and it shows why ambiguity cannot be completely eliminated. This duality is not a failure. It is a balance. Human thought needs both rigor and intuition, both structure and flexibility. Math, at its best, uses intuition to discover ideas and rigor to confirm them. The problem arises when we expect rigor to replace intuition entirely. That is when things become heavy, form overwhelming. And this is why most mathematicians do not work the way Russell and Whitehead did. They stand on the foundations that were built. They trust the system. They focus on creativity rather than justification. They allow themselves to say, "It's obvious," when it really is. And that is okay, because the foundations have been checked. Not every generation needs to rebuild them. The human brain, thankfully, is capable of both modes. We can overthink when it matters, and relax when it doesn't. The mistake is believing that only one mode is valid. Russell believed clarity was morally important. Gödel showed that clarity has limits. Together, their work paints a picture of human cognition that is both ambitious and humble. We want to know everything, and we have to accept that we can't. This acceptance is not defeat, it is maturity. So when you hear that it took 360 pages to prove 1 + 1 = 2, it is tempting to laugh, and laughing is fine. But behind the joke is a very human story, a story about minds that refuse to be satisfied with because, a story about the lengths we will go to feel secure, a story about the beauty and the cost of overthinking. And perhaps the most comforting lesson of all is this: even when we overthink, even when we build enormous systems, even when we chase certainty to its limits, the world does not collapse. 1 + 1 still equals 2. Bridges still stand. Sheep still get counted. Life goes on, which means that maybe, just maybe, it is okay to let go sometimes, to trust what works, to accept that not everything needs to be proven tonight. And with that thought, we are almost ready to rest. Because after all this effort, after all this thinking, after all this careful reasoning, there is something deeply soothing about returning to simplicity, about remembering that you do not need to prove 1 + 1 = 2 in order to sleep peacefully. And that realization brings us to a very gentle conclusion, one that does not demand rigor, one that does not ask questions, one that simply reassures, which is where we go next, to the quiet reminder that you personally do not need to prove anything at all. After everything we've talked about, it is important to say this clearly. You do not need to prove 1 + 1 = 2. Not tonight, not ever. You are allowed to use it. You are allowed to trust it. You are allowed to let it be obvious. The 360-page proof was not written for daily life. It was not written for counting groceries, checking the time, or figuring out how many pillows are too many. It was written to satisfy a very specific kind of curiosity, the kind that does not like loose ends. Most of the time, that kind of curiosity is unnecessary, and that is not an insult. It is a relief, because life is complicated enough without rebuilding arithmetic every morning. Imagine if you had to justify everything you trusted. Why the floor holds you. Why words mean what they mean. Why tomorrow will look roughly like today. You would never rest. Human life depends on trust, on shared assumptions, on ideas that work well enough to carry us forward. Math, despite its reputation, is no different. When you use arithmetic, you are standing on a foundation built by generations of thinkers, some of them worried about definitions, some of them worried about paradoxes, some of them worried enough to write 3-volume books. You do not have to worry anymore. The checking has been done. The system holds. You can count sheep without defining sets. You can add numbers without invoking logic. You can live comfortably without knowing anything about Principia Mathematica. This is not ignorance. It is delegation. We delegate certainty to experts all the time. We trust that bridges are built correctly. We trust that medicine works. We trust that clocks tell time. Not because we personally verified every detail, but because systems exist to handle that work. Math is one of those systems. The fact that someone once proved 1 plus 1 equals 2 does not mean you are expected to understand that proof. It means you are free not to. There is also something quietly beautiful about this. The deepest foundations of math exist far below the surface. They are invisible, and that is exactly how foundations should be. You do not stare at them. You do not interact with them directly. You walk on them. This is why most mathematicians do not care about foundational proofs on a daily basis. They care about ideas, patterns, connections, creativity. The foundations are important, but they are not the focus. And that balance is healthy. It is okay to overthink sometimes. It is also okay to stop. Russell could not stop. That was his gift and his burden. You are not required to inherit that burden. You can enjoy the result without reliving the process. You can trust that 1 plus 1 equals 2 because it always has, because it always will. Because if it didn't, something much bigger than mathematics would have gone wrong. There is also a deeper reassurance here. The fact that such a proof exists does not make the world more fragile. It makes it more stable. It means that even our most basic ideas have been examined with extraordinary care, that they have survived scrutiny, that they hold up under pressure. This does not mean they need to be questioned again. It means they don't. And this is why the story of the 360-page proof is ultimately comforting. It shows that humans care enough to check, enough to worry, enough to ask why. And once the asking is done, we can relax. We can let the obvious be obvious again. There is no danger in trusting addition. There is no hidden trap waiting to collapse your everyday reasoning. The paradoxes live far away, in abstract systems most people never visit. Your world is safe. Your arithmetic is safe. Your intuition is safe. And even if math has limits, those limits do not affect your ability to live, think, or sleep. In fact, recognizing limits can be soothing. It means you are not expected to know everything, not expected to justify everything, not expected to chase certainty to its final edge. Some things are allowed to simply work, and 1 plus 1 is one of them. So as we begin to slow down, it helps to remember this. The story you have been listening to is about extremes, about people who pushed ideas as far as they could go. You are not being asked to follow them all the way. You are being invited to appreciate the effort, and then step back to enjoy the view from a comfortable distance, to smile at the absurdity, to feel reassured by the outcome, and to let go, because at the end of the day, after all the pages and proofs and paradoxes, arithmetic remains one of the most stable things we have. It works quietly, reliably, without drama. It does not demand your attention. It does not ask to be admired. It just does its job, which is exactly what you want from something that supports so much of daily life. So you can let the mathematicians have their arguments, let the logicians have their symbols, let the philosophers have their debates. You can rest. You can trust that when you wake up tomorrow, 2 will still be 2, 1 plus 1 will still be 2, and nothing important will have changed. That knowledge does not require proof. It requires acceptance. And acceptance, unlike certainty, is something you can enjoy without effort, which makes it the perfect place to slow down, to stop questioning, and to prepare for something much quieter. Because now that the reassurance is complete, there is nothing left to solve, nothing left to justify, nothing left to prove. Only the gentle satisfaction of knowing that the simplest truths are still holding everything together. And with that in mind, we can move into the final stretch. Not with arguments, not with logic, but with something softer. A reflection on why thinking too much can sometimes be beautiful, and why it is also okay to stop thinking altogether, which is exactly where we are headed next. Overthinking has a bad reputation. It is often blamed for anxiety, indecision, and long nights staring at the ceiling. And to be fair, that criticism is earned. But overthinking also has a softer side, a quieter side, the side that lingers with an idea not because it is useful, but because it is interesting, the side that enjoys turning a thought over and over, just to see how it looks from different angles. This is the kind of overthinking that built mathematics, not the rushed kind, not the panicked kind, the patient kind, the kind that sits with a question long after it has stopped being necessary. The story of proving 1 plus 1 equals 2 is in many ways a love letter to this version of overthinking. No crisis demanded it. No one needed the proof. No practical problem required it. It existed because someone cared enough to ask, and then cared enough not to stop. There is something almost meditative about that. To take a simple idea and examine it slowly, to remove assumptions, to rebuild it piece by piece, not because you are lost, but because you want to know where you are standing. This kind of thinking is not loud. It does not rush. It does not demand attention. It unfolds quietly over years in notebooks and long discussions. It is not efficient, but it is gentle. And that gentleness is easy to miss when we focus only on results. When we talk about the 360-page proof, we often frame it as excess, as a joke, as an example of intellectual absurdity. But there is another way to see it, as patience, as care. Imagine loving a concept enough to examine it that closely, as respect for an idea, to refuse to take it for granted, to want to understand it completely. There is something tender about that. Mathematics at its best is not about domination or control. It is about attention, about noticing patterns. This is why many mathematicians describe their work as peaceful, about staying with a thought long enough for it to reveal itself. Not exciting, not dramatic, peaceful, long stretches of quiet thinking, moments of clarity, a sense of order emerging slowly. The proof that 1 + 1 = 2 fits into this tradition. It is not flashy. It does not try to impress. It simply exists, quietly confirming that the structure holds, and that quiet confirmation is deeply satisfying, not in a dramatic way, in a grounding way. When it becomes a desperate attempt to control uncertainty, overthinking becomes a problem when it turns into fear. But overthinking can also be a form of curiosity, a way of exploring ideas without pressure, without urgency, just because they are there. Russell and Whitehead were not afraid when they wrote Principia Mathematica. They were focused, absorbed. They were not chasing answers for survival, engaged. They were chasing understanding for its own sake. Humans think when they do not have to. They wonder. And that is a very human thing to do. This is where art comes from. They reflect. They ask questions long after the practical need has passed. Where philosophy comes from, where stories like this come from. The fact that mathematics contains space for this kind of thinking is comforting. It means that even in a field known for precision and rigor, there is room for slowness, for patience, for thought that is not immediately useful. The irony is that this kind of overthinking often leads to clarity, not because it is efficient, but because it is thorough. You allow understanding to arrive naturally. When you take your time with an idea, you remove pressure, and sometimes that is exactly what the mind needs. It is not trying to convince you of anything, which is why this story works so well as something to fall asleep to. It is not asking you to solve a problem, and how gently it can return. It is simply inviting you to observe how far human thought can wander. After all the definitions, the proofs, the paradoxes, and the philosophies, we end up exactly where we started, with 1 + 1 = 2. Nothing has changed, and yet everything feels calmer, because now you know that the idea has been examined, that it has been held up to the light, that it has survived scrutiny. Overthinking, when it reaches its natural end, turns into rest, and that you do not need to think about it anymore. The mind relaxes, the question dissolves, the idea settles into place, and that settling is what sleep feels like, a release, a quiet acceptance. So if you feel your thoughts slowing now, that is not an accident. This story has been gently winding down, not by removing complexity, but by resolving it, by showing that even the most intense intellectual efforts eventually lead back to simplicity. That thinking deeply does not trap you forever. It brings you home, and home, in this case, is a very small idea. 1 + 1 = 2. Simple, to stable, unchanged. It has been with us for thousands of years. It will be with us tomorrow, and it does not require your attention. You can let it sit quietly in the background, doing its job. You do not need to check it. You do not need to question it. You do not need to rebuild it. It is there, and that is enough. As the thinking slows, as the mind releases its grip on questions, there is a gentle comfort in knowing that some truths remain steady, no matter how deeply you examine them. that even after hundreds of pages of reasoning, the simplest ideas still stand, that overthinking, when done with care, leads not to chaos but to calm. And with that calm, we are ready for the final step. Not a conclusion, not a summary, just a return to the beginning, to the simplest truth, to a place where nothing needs to be proven, only accepted, and that is where we will finish. Quietly, gently, at rest. We have travelled a very long way to arrive somewhere very small. A single idea, 1 + 1 = 2. At the beginning it felt so obvious that it barely seemed worth mentioning. At the end, after centuries of thought, thousands of pages, paradoxes, dreams of certainty, and a 360-page proof, it still feels exactly the same. That is comforting, because it means something important. Survived the journey. Not the proof, not the logic, not the symbols, but the idea itself. The truth did not change. Only our relationship to it did. At first, 1 + 1 = 2 was something you felt, then it became something you used. Then it became something you questioned, then something you justified. And now, finally, it becomes something you can let go of. The story ends where it began, not with a dramatic conclusion, not with a final argument, but with acceptance. The mathematicians did their work. They worried, they defined, they proved, they pushed certainty as far as it could go, and when they reached the limit, they stopped. That stopping matters, because knowing where to stop is part of wisdom. Russell could not stop until the foundations were checked. Gödel showed that the checking could never be complete, and mathematics learned to live with that, not as a failure, but as a fact. And in that acceptance, something gentle appears. A calm understanding that not everything needs to be nailed down forever, that some truths are strong enough to carry us without constant inspection. 1 + 1 = 2 is one of those truths. It does not wobble. It does not demand attention. It simply works. It worked when people counted sheep. It worked when builders measured stone. It worked when philosophers argued. It worked when logicians formalized. It worked before the proof. It worked after the proof. And it will keep working long after this story fades into silence. There is something deeply soothing about that. The world can be complex. Thought can be heavy. Questions can multiply endlessly. But some things remain stable. Some ideas are quiet anchors. You do not need to think about them for them to hold. And as the thinking slows, as the layers peel away, what remains is simplicity. Not the simplicity of ignorance, but the simplicity of resolution. The feeling that nothing more is required. Nothing more needs to be explained. Nothing more needs to be justified. You can rest here, with the idea that knowledge does not need to be loud to be reliable, that certainty does not need to be absolute to be useful, that understanding can coexist with mystery, and that even after the deepest thinking, the simplest truths remain unchanged. If your mind is still holding on to fragments of the story, that is okay. They can drift. They do not need to connect anymore. The narrative has done its work. The questions have been answered as far as they need to be. What remains is not a problem to solve, but a space to settle into. Think back to the beginning, to the comfort of obvious things, to the quiet confidence that some ideas simply hold the world together. We left that place briefly. We wandered. We examined. We built elaborate structures of thought. And now we return, not because the journey was unnecessary, but because it is complete. 1 + 1 = 2. It did not change. We did. We learnt that certainty can be explored without being destroyed, that overthinking can lead back to calm, that even the most intense intellectual efforts eventually point toward rest, and rest is the final result. So if your thoughts are slowing now, that is exactly as intended. There is nothing left to chase, nothing left to check, nothing left to prove. The simplest truth has survived every question. It does not need your attention anymore. You can let it sit quietly, like a familiar object in a familiar room, always there, never demanding. And as the thinking fades, as the edges of the story soften, you can allow yourself to do what humans have always done after counting their sheep. You can stop counting. You can stop questioning. You can stop building. And you can sleep. Because in a world full of complexity, It is enough to know that some things remain simple, that 1 plus 1 still equals 2, that the ground beneath the ideas is solid, and that for now, and for tonight, that is all you need to know.